Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Very good morning. Today we are talking about nonlinear regression model. Okay, in the previous classes we discussed about linear model. So now we are talking about nonlinear model. Okay, when we started our discussions of linear regression model in chapter 2, we started that our concern in this book is basically with the model that are linear in parameters. Okay, this is one of assumptions in the classical linear regression model. They may be, may not be in linear in variables. Okay. If we look at the table 3, 2, 2, 3, you will see that the model that is linear in parameters as well variable is linear regression model. Okay. So it's okay. On the other hand, if a model is nonlinear in parameters, it is clear that is a nonlinear parameter regression model, whether the variables such as a model they are linear or nonlinear. Okay. In the nonlinear model, we can have nonlinear parameters also in nonlinear in variables. Okay, however, one has to be careful here for some models look nonlinear in parameters but are inherently or intrinsically linear because with the suitable transformations. For example, in the Coupler class production function model, the model is nonlinear, but if we transform the data into log terms, so we will have linear regression model. Okay, here the example for the model. Okay, this one, for example, this is equations 14.1.2. This is Coupler class production function model. If we take log term, we transform into log term. So the equation 14.1.2a become linear model. Okay, here we have beta 2 and beta 3 as elasticity. Okay, if you estimate your model in a log term, both sides, that's mean log model. Okay, that means you have beta 2 as elasticity of x2 and beta 3 as elasticity of x3. Now this is a CES model, constant elasticity of substitutions. This is the special case of Coupler class model. Here, for example, K is capital, L is label, A is a scale parameter, delta is a distribution parameter, delta run from 0 until 1. Beta is a substitution parameter. Okay. Equation 14.1.5 is a nonlinear regression model. To see the difference in estimating linear and nonlinear regression model, considers for the following models. We have 14.2.1 and 14.2.2. Okay, equation 14.2.1 is a linear regression model because the parameters has to the power 1. Okay. Meanwhile, equation 14.2.2 is a nonlinear regression model because we have here exponential regression model. Here, beta 1 times epsilon to the power beta to x2. So this model actually is a gross model. It's commonly used in the to calculate the growth rate. For example, what is the GDP or population growth rate? Suppose we consider estimating the parameter of two models by ordinary least square. Can we minimize the equation 14 to 1? Okay, so we take here, take the derivative of this equation 14 to 3 with respect to beta 1 and beta 2. So we get the coefficient of beta 1 and beta 2. Now if we take another equations, okay, for example, for this 42 2. If we try to minimize residual sum of square of equation 14 to 2, okay, as stated in appendix 14a, section A1, 14A1, normal equation corresponding to equation 314 and 315 as follows. Okay, this is the equations. Okay, here, unlike the normal equation in the case of linear regression model, the normal equation for linear regressions have the unknown betas. Both sides we have in the left hand side and the right hand side of betas. Okay, as a consequence, we cannot obtain explicit solutions. Okay, in equation 14, 14 to 3, we can solve the equations because beta only on the right hand side. However, for equation 14 to 4 and 14 to 5, each equation has betas in the left and in the right of the equations. Okay, so this is nonlinear regression model. We cannot apply the OLS to obtain the beta 1 and beta 2. Now, how to estimate the nonlinear regression model? To set the stage that as considered a concrete example, we use the data in the table 41 to manage management fees and the leading mutual fund in the United States pays to its investment advisors to manage its asset. The fees paid depend on the net asset value of the fund. We can see here for the data. This one, data. Okay, fees, yeah, depend on the asset. Okay. To see how exponential regression model in equation 14.2.2 fits the data given in table 14.1, we can draw the data into this graph. Okay, so if we look at the graph here, the relationship between fees and asset is non-linear. Okay, and now we can proceed by trial and error. Suppose we assume that initial beta 1 is 0.45 and beta 2.01. These are pure guesses. This is not actually based on the calculations. Sometimes based on the period experience or period empirical works that have been done by other parties. Okay. And we fit the linear regression model, even though we might not be appropriate model. As in this stage, because we impose beta 1 and beta 2 in equations 14 to 1 and 14 to 2. Okay, we get here. Okay, we have residual here. Residual of the equation is in equation 14.3.2. Okay, since yx and beta 1 and beta 2 are unknown, we can easily find the error sum of square in equations 14.3.2. Okay, here our objective is to solve this problem, to find the value of parameters. So now we take the derivative of equation 14.32. Okay, y value from the model are close as possible to the y values. With the given values, we obtain the sigma square is 0.34044. But how do we know that this is a least possible error sum of square? Because we only impose the coefficient beta 1, beta 2. Okay. Now, what happens if we choose another beta 1 and beta 2? For example, we have 0.5 and minus 0.01. Repeating this, the same calculations, we get sigma square is 0.0073. Okay. Now here we have smaller sum of square, residual sum of square compared to the previous one. Now this is time consuming because the method is based on the trial and error. Okay, we have to calculate several times to get the best values for residual sum of square. So we do not need to do this one. We have to find out the more appropriate method to estimate the coefficient of nonlinear regression model. Okay, there are several approaches nonlinear regression model: direct search or trial error, time consuming, direct optimizations, and iterative linearization. Iterative linearization, that's when we have to also recalculate several times. Okay, direct search or trial error, and derivative free method. In the previous sessions, we showed that how this method works, although intuitively appealing because it does not require the use of calculus method, as in the linear regression model. This method generally not used. Why? First, if an nonlinear regression model involves several parameters, for example, we have 3 or more variables, okay, the method becomes very cumbersome and computationally expensive because we need more time to solve the problem. For example, if we have 5 parameters here, okay, we have 25 alternative values for each parameter. Okay, if we have 25 to the power 5 is almost 10 million times you have to calculate. Second, there is no guarantee that the final set of parameter values you have selected will necessarily give you the absolute minimum error sum of square. So it is not recommended to use in this regression model. Direct optimizations. In direct optimization, we differentiate the error sum of square with respect to unknown coefficient or parameter, setting the results equation to 0. I explained already to you. We have to minimize or maximize an equation. So we have to take the first derivative as first order conditions, and we have to the equation, the result from the equation should be set to be 0. Okay, we have already seen in the equation 14.24 and 14.25, but as you can see from the equation, they cannot be solved explicitly or analytically. Some iterative routine is therefore you have to do some iterative, for example, several times calculations. Like the method of trial and error, the method of steepest descent also involves selecting initial trial values. So if we choose a wrong number, we have to calculate again to obtain or to have the minimum residual sum of square. One disadvantage of the method is that it may converge to the final values of parameter extremely slowly. Okay, I explained already, if we have more parameters, that means we need more time to solve these equations. Iterative linearization method. In this method, we linearize a nonlinear equation around some initial values of the parameters. The linearized equation is then estimated by OLS, and initially chosen values are adjusted. These adjusted values are used to realize the model, and again we estimate by OLS. So we have to choose also the initial value of the parameters. This process is continued until there is no substantial change in the estimate values. That means we have the convergence parameters of the model. The main technique used in linearizing a model equation is Taylor series expansions from the calculus. Okay, so this also time consuming to calculate these equations. Okay, we continue with the qualitative response regression model. Okay, most of students now use these types of regression model. Okay, in all regression models that we considered, we have implicitly assumed that the regressions, the dependent variables of response variable is quantitative. Okay, now if we use this dependent variable as qualitative or dummy variables, how to deal with this model? Okay. Okay, for example, if we want to, this is reference for samples. Okay. One, for example, is respondent. Okay, respondents prefer to use Samsung. That's it. Zero otherwise. Okay, here we can estimate this model. Okay, here mobile phone is determined by income and price of Samsung, for example, price of other mobile phone, okay. And here we have a family size expectation. Okay. Expectation. Okay, we only have 6 variables. Here MP mobile phone for Samsung. Okay, if 1 is Samsung and 0 is otherwise. Okay. Okay. Here LFP cannot be estimated by using OLS because the model is non. Okay. Here we have a dependent variable as qualitative variables. Okay. Here we suppose we have labor force participations. Okay, decision of adult males. Since an adult is either in labor force or not, labor force participation is a yes or no decision. Okay, hence the response variable of regression can take value 1 if the person is in the labor force, 0 is otherwise it's not in the labor force. In other words, the regression is a binary dichotomous variables. Labor economics research suggests that LFP decision is a function of unemployment rate, okay, average wage rate, educations, family income, and other variables. Okay, this is the model of nonlinear one. Okay, another example here: U.S. presidential elections. Assume there are two political parties, Democratic and Republican. The dependent variable is a fourth choice between the two political parties. Suppose if we take value 1 for the Democrats and 0 for otherwise. Okay, this is another model of nonlinear one. Okay. For the present purpose, the important things to note is that the regression is qualitative variables. Okay, here we have qualitative dependent variables. So we cannot estimate this model directly by OLS. One can think of several other examples where the regression is qualitative in nature. Okay, for example, family that wants to buy a car or not. Okay. Family either they owns a house or not. Is a disability insurance. It does not. Both husband and wife are in the labor force, or only one suppose is. Similarly, a certain drug is effective in curing an illness or it is not. Okay, this is some examples of nonlinear regression model. Okay, now we continue our discussions. Okay, there are several models here in this. We call it a linear probability model, LPM. Okay, we have logit model, we have probit, we have tobit. Okay, there are 4 models in this nonlinear one. Because of its comparative simplicity and because it can be estimated by ordinary least square, we will start consider linear probability model. Okay. Here we actually, if we want to estimate or this linear probability model, we have to transform the data into linear model. Okay. Here we have equation 15:1. Okay, X is a family income. Y if the family owns a house and 0 otherwise. Model 52:1 looks like a typical linear regression, but because the regression is binary or dichotomous, it's called linear probability model. This is because conditional expectation Y given on the values of X. Okay, the conditional probability that event will occur given X, that is the probability y is 1 conditionally with the value of x. That is our example. Expected value of y, conditional expected value of y with the given value of x, okay, is the probability of a family owning a house and whose income is the given amount of x. Okay, the justification of the name of linear probability model, the question 15 to 1 can be seen as follows. Assuming that the residuals from the equation 15 to 1 is white noise, okay, this is unbiased, okay. Now, if pi, probability that y is 1, that is the event occur, and 1 minus pi is the probability does not occur. Okay, here we have this one. 1, that means pi. 1 minus pi, that means 0. Okay, y follows the Bernoulli probability distributions. Now, by definitions of mathematical expectations, expected value of y is 0 times the probability plus 1 times the probability. This means it's equal to pi. Comparing equation 15 to 2 with equation 15 to 3, we can equate these equations. Okay, this means expected value of y with a conditional value of x, it is same as the probability of the occurring. Okay, in general, expectations of the Bernoulli random variable is probability that random variable equals 1. Implying that if there is an independent variables is with the probability p of success and probability 1 minus p for failure. Okay, x is the trial represent the number of successes. X is said to follow the binomial distributions. The mean of binomial distribution is n by p. N is a number of sample. Okay, p is a probability, and its variant is np times 1 minus p. The success is defined as the context of the problems. Okay, since the probability pi lie between 0 and 1, we transform the expected value of y with the conditional value of x. This means this value goes from 0 until 1. Okay, from the preceding discussion, it was seen that OLS can be easily extended to binary dependent variable regression model. So we have to transform the equations with some calculations. Okay. Now, although OLS does not require the disturbances to be normally distributed, we assume them to be so distributed for the purpose of statistical inferences. But the assumptions of normality for the residuals is not tenable for the linear probability model, because yi distribution mu I also takes only the two values, that is also follow the distributions of Bernoulli. Okay, this is the probability when y is 1, so the residual is 1 minus beta 1 minus beta 2x, which the probability is pi. When y is 0, this means the residual is minus beta 1 minus beta 2x I with the probability 1 minus pi. Okay, mu I cannot be assumed to be normally distributed. They follow the Bernoulli distributions. Okay. But the non-fulfillment of the normality assumptions might not be so critical, okay, as it appears, because we know that OLS point estimates still remain unbiased. Okay. Besides, as the sample size increase to huge samples, for example, okay, statistical theories show that OLS estimator tend to be normally distributed. If the OLS has normal distributions, so this means we can use the OLS model to estimate the coefficients of linear probability model. Okay, large samples properties, statistical inference of linear probability model will follow the usual OLS procedures under normality assumptions. Okay, if we have large samples, so we can easily use the OLS to linear probability model. For distribution of the error term given in equation 15.2.5, applying the definitions of variance. Okay, this is a variant. Variant is pi times 1 minus pi in equation 15.2a. Okay, the variant of error term in linear probability model is heteroscedastic. Okay, since pi is an expected value of conditional mean, we have beta 1 plus beta 2 xi. The variant of mu I ultimately depends on the value of x, and hence it is not homoscedastic. Okay, this means the value will become bigger and bigger if the value of x increase. We already know that in the presence of heteroscedasticity, OLS estimator, although unbiased, but the coefficient become inefficient. Okay, because the coefficient, the parameter, do not have a minimum variance. Okay, if the problem on only the heteroscedasticity, actually we can directly use the OLS. However, the problem of non-normality is not instrumentable. In chapter 11, we discussed several methods of handling heteroscedasticity problem. We can transform the data to be weighted variables. So we can, after transforming the data into weighted values, we can use directly the OLS method to estimate the parameters of equations. Okay, this is same as the weighted variables. Okay, we divided all variables with the yi is weighted variable. Okay, after we transform the data, so we can use OLS directly. Okay. Okay, here, for example, we have the data here. This is y has only two values, 1 and 0. Okay. Okay, here, for example. Okay, we have to transform the data here. Let's transform data. Okay, become y hat. Okay, we anticipated to Here, this is the probability here, 0 and 1. Okay. Okay. To illustrate some of the point meant by the about the linear probability model, we present a numerical examples about 15.1. We give the invented data on the home ownership. Y if the family has a house, 0 otherwise. X is a family income. Here there are 40 families. Okay, we estimate the LPM by ONS. We get this one. Okay, let us interpret the regression. The intercept term coefficient is minus 0.9 something. This is the probability that a family with a 0 income, that means if income is 0, so the family has probability will own house. Okay, since the value is negative, okay, since the probability cannot be negative, we treat this value as 0 because this is negative, which is sensibly the present instance. Okay, the slope value of family income is 0.1021, means that for a unit change in income, for example here 1,000, on average the probability of owning a house increased by 0.1021 or about 10%. Okay, of course, given the particular level of income, we can estimate actual probability of owning of our house. For example, here if X is 12,000, okay, the estimated probability of owning house is 25%. Okay, if income 12,000, that means the probability to have house is 20%, 28%. Table 15.2 shows the estimated probabilities, yeah, Y hat, for the various income level. The most noticeable feature of this table is that 6 estimated values are negative and 6 values are in excess of 1. Okay, here we have negative, okay, and also the probability greater than 1. Okay, here, this one. Okay, here again, you can see in the table of table 15.2. Okay. Even if the estimated value Y are all positive and less than 1, the LPM still suffer from the problem of heteroscedasticity. Okay, we can see from the equation 15.2a. As a consequence, we cannot trust the estimated standard error in equation 15.210. Okay, we can look at the 15.210. Yeah, this R square actually is very good. Yeah, 0.8. But okay, we can use the weighted least square procedures discussed in the previous chapter to have the more efficient parameters. Okay, we have to calculate the WI as a weighted value. Because Y some are negative and some so positive, okay, WI corresponding to this value will be negative. Thus, we cannot use these observations in WLS. Why? Because the value, some of value are negative values. Therefore, reducing the number of observations from 40 to 28 in the present example, we omitting these observations, so our regression is become this one. Okay. Here R square is bigger than previous one. Okay. Now it is still negative here, but this one is almost the same. It's around 10%, here 12%. This results so that compared to equation 15 to 10, the estimated standard error are smaller. If we have smaller standard error, that means we have more efficient parameters. Okay, but one should take this result with grain Salsian's estimating equation 15 to 11. Okay, we drop 12 observations. Okay, and we also transform the data into weighted square model. Okay, I can skip this one. Alternative to LPM. Okay. Okay, we have here problems, non-normality of residuals, heteroscedasticity, and we have a possibility that Y has like Y has outside values. Okay. And usually in the qualitative regression model, we have fairly low R square. Okay, this is the cumulative distributions model. Okay, here is a 0.5 here, half. This is 0. This is a 1. So usually I use a logic model to estimate the qualitative regression model because we need more time to transform the data into weighted square, and some of data have negative values, so it is better to use the logic model. So here we continue with the same example, the home ownership determined by the income. Okay, this is probability. X is income. Probability means that family has owned is with the if Y is 1 with the conditional probability of income. Okay, here PI is 1 over 1 plus E. Okay, we have this natural log values base. Okay, the value of this is this is a repetitive number 1828, 1828. Okay, this is the values of epsilon. Okay, so now here we transform our equations. For example, here for easy of expositions, we write the equation. This equation become this one. Now Z is beta 1 plus beta 2 xi. Okay, equations 15.5.3 represent is unknown cumulative logistic distributions functions. Here the distribution is logistic distributions functions. Okay. Okay, it is easy to verify that as Z ranks from negative unlimited to positive, PI ranges from 0 and 1. Okay, P is non-linearly related to Z. Okay, thus satisfying the two requirements considered alien. But it seems that in satisfying this requirement, we have created an estimations problem because pi is non-linear, okay, but x is linear. X also in to the power of betas. This means that we cannot use OLS directly to estimate this problem. Okay. Now we have here 1 minus pi. This means the family doesn't have the house. Equation 15.54, and we have equation 15.55. Now pi over 1 minus pi, this is the probability, this is the odd ratio. In favor of owning a house, there's the ratio of probability that a family will own a house to the probability it will not own a house. Thus, if the value of a probability is 0.8, that means that there are 4 to 1 in favor of family owning a house. Okay, here we take the log, natural log of these equations. We have this one. Now, Z is a linear one. Linear. Okay, L is log of odd ratio. It's not a linear in X, but also not only linear in X, but also in the parameters. Okay, L equal to logic, hence the name logic model. Okay, notice this feature of the logic model. As P goes from 0 to 1, okay, so the logic goes from minus to positive unlimited. They say although the probability lies between 0 and 1, the logics are not bounded. Although L is a linear in X, the probability themselves are not. Okay, this property is not contrast with the linear probability model. Although we have included only a single X variable or regressors, the preceding model. Okay, in the preceding model, one can add many variables in the model. Okay. Okay. The L is logic is positive. It means that when the value of regression increase, the odds that the regression equal to 1 increase. If L is negative, the odds the regressions equal to 1 decrease as the value of X increase. More formally, the interpretation of logic model in equation 15.56 is follow. Beta 2 slope measure the change in L for a unit change in X. Tell how the log odds in the favor of owning a house changes as income changes by a unit. Say here, for example, 1,000. The intercept beta 1, the value of log odds in favor of owning house if income is 0. Okay, now we can estimate this one. For example, we have equations 15.61. Okay. Okay, we cannot directly use it like this. Okay, we cannot use directly. Okay, this group data. Okay. Now group logic. Okay, I want to show you how to estimate the logistic model. Yeah, we need time to open this software. Okay. Can you see this SPSS?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now, for example, I will use my data. This is a real data. Okay. This is my research actually. Okay. Okay, this is my research. Okay, I'm still writing. Okay, I have several variables here. I have sample here around 591 samples. Okay, I have variable here from the 36 variables. Okay. Now, for example, I want to estimate this logistic model. And first, okay, this one, the choice of family to the preferences of household. To use financial technology or fintech. Okay. Okay, here we choose self-analyze. From analyze, we take regressions. Okay. Then we choose binary logistic. Okay, we choose binary logistic. Here I will take the dependent variables. Dependent variable here is the respondent use fintech. Okay, and then I will use genders as independent variables. Okay, this is educational educations, years of schooling. Okay, I will choose years of schooling, display tracing. Okay, years of schoolings. Yeah. Family size, income per capita. Okay. And then I have here okay, sorry, I have incoming call for Y. Okay, if you choose here option, for example, okay, you can take the correlations estimate, iteration history. Okay, this is confidence interval for beta. Okay. Continue here. Okay, categorical, we don't have categorical here, and I have to continue. Okay, this is the dependent variable has more than 2 unknown missing value. Okay, sorry, we have to rerun again. Actually here, I choose here income, not family size, years of schooling. I change to educational levels. Why? Because the dependent variable, problem in the dependent variable. So here, Okay, here's our equation, estimated variables. Now we have gender, family size, income. Okay, this is a significant level. Only gender is significant and educational level. Income and family size are not significant statistically, but theoretically, yes. This is a history for the iterations. This is a constant from 1 point something until 2 point something. Income here, okay, I want to re-estimate again by choosing this income with the per capita income. Oh, actually, I missed this one. This working status. You know, I have to use working status here. Okay. Family size is inside already. Income per capita. Educational level, poverty level. Poverty. Okay. And gender, family size, educational level, income per capita, poverty status. Okay, here, working status. I forgot to calculate this one. Okay. Okay, this one, gender is significant, educational level significant, poverty significant, but family size is not significant. We have two variables are not significant, family size and income per capita. Okay. However, because we use already this poor status, okay, actually we do not need this one, income per capita, because income has been transformed into poverty level. So we run again this one. Okay, here. Now I think it's better. Only family size is not significant. Educational level significant. Poverty significant. Okay. Gender is also significant. Okay. Any question here?
I have a question about the results of the SPSS. Like it's apparently different from EView. So I don't know, like I heard you saying income is significant, and like I can't see those values here. Like I don't know how to read this.
Okay, it actually is the same. Okay, in SPSS is better in terms of qualitative model, but if use is more advanced in time series model. Okay, now I want to show you the equation. This is one of the equations, variable in the equation. If you make a report in your thesis, this one is coefficients of gender in -1. Okay, this is a standard error. This is a significant level. You see here, 6 is IG here, significant level, 0.000. This means this one less than 5%. This means it is significant. Okay. Family size here, for example. Family size is a negative, also negative coefficient, but it's not significant. Educational level is significant because it has 0.001. Okay, poverty status is not significant. Okay, any other question? Okay, I want to explain you how to, I explain this one, how to read or to interpret this one. Okay, we have also here another one is a expected value of beta here. This is from beta here, expected value. This means this in, okay, gender, for example, if here we have 0.321, 9. Okay, this means if male, the coefficient of gender is 1 is male, 0 otherwise. This means 0 is female. If 1, that means the probability to choose financial technology, if male, become lower because this coefficient is negative, lower about 0.329. Okay. Any other question? No?
Awesome.